this lesson today, we're going to discover the wonderful world of quadrilaterals. Over the next 3 lessons altogether, we will break it up and specialize in various types of quadrilaterals and show the properties they contain, the relationships, and some brand new theorems, and some very important facts that kind of accumulate actually from some previously learned theorems and postulates. First of all, a quadrilateral is a general name for a plane 4-sided figure. Or in other words, it is a polygon, which is a plane figure with 4 sides. A quadrilateral is a plane 4-sided figure, or a polygon with 4 sides. A quadrilateral contains a total of 360 degrees. We can show that by showing this way. We know that if we have a regular quadrilateral, such as this, just a plain old quadrilateral, if we divided this up with a diagonal such as this, it divides it into 2 triangles. Each triangle contains, as we learned, 180 degrees. So 180 degrees plus another 180 means a total measure of 360 degrees. So therefore, that's how we can say that all 4-sided figures, all quadrilaterals, contain 360 degrees. Now, to keep all this in perspective, I want to refer to this family tree of quadrilaterals. This will kind of help us keep things in mind and kind of keep our bearings where we are so we won't get lost. You want to know maybe how one relates to the other or how one evolves from the other? Let's refer back to this family tree many times and keep our bearings straight. First of all, the general family of quadrilaterals is just, as I said, defined as a plane 4-sided figure, or a polygon with 4 sides. We have various branches off from that, just like, as it says, a family tree. It has certain characteristics down here that evolve from the quadrilateral. These over here have certain different characteristics that evolve from the quadrilateral, but they have some new properties too that keep them separate from this family down in here. And then over there by itself we have the family of kites, and they are separated from the others by their own unique set of properties. So this family tree of quadrilaterals will help us, I think, keep things straight as we go through the next 3 lessons. So we need to refer back to this from time to time. Just like, in your family tree, you have certain family characteristics. You say, oh yeah, you must be one of the Smith family. You all have those pretty eyes. You all have those same family characteristics. Well, these are the same way. They'll have some of the same characteristics from some of these quadrilaterals above in this descendants of order here. So, first of all, we're going to talk today about the parallelograms in this lesson. The parallelograms, right in here. This is where we are. So again, it is simply a plane 4-sided figure, and its definition is it's a quadrilateral with 2 pairs of opposite parallel sides, and thus its name, parallelogram. fresh in our mind. And again, by drawing that diagonal, and we've got the parallelogram with opposite sides parallel, once again, angle 1 here and angle 4 would be congruent, alternate interior angles. Angle 3 and angle 2 would be congruent, alternate interior angles. And again, a common side between them, between the two triangles. So once again, the triangles are congruent by angle, side, angle, and therefore, angle A would be congruent to angle C because they're corresponding angles of the two congruent triangles. And angle D, which now has been chopped up by this diagonal, so we should call it actually angle ADC, the entire angle would be congruent to this entire angle, ABC. So there again, that would be the original angle D and the original angle B congruent as well. The diagonals of a parallelogram bisect each other. The diagonals of a parallelogram bisect each other. So given, again, all we know is it's a parallelogram. But again, now we've accumulated some more ammunition. We've got a couple other theorems as well before this one to help us prove what we need to prove and develop new theorems. So, if it's given as a parallelogram, we've got to prove here that the diagonals bisect each other. That would be to say, in other words, that that segment and that segment are equal in measure, and therefore they are bisected by the green diagonal. And also we need to say then that that segment and that segment are equal in measure, or congruent. And therefore they're bisected by the shorter red diagonal. So, to prove this, let's go through this. We haven't taken a proof for a while here, so let's say it's given we have parallelogram ABCD. That is given. And because it is a parallelogram, then we know that opposite sides are parallel, so we know that DC is parallel to AB. And also we could say that AD is parallel to BC. That's by simply the definition of a parallelogram. Definition of a parallelogram, which says, of course, opposite sides are parallel. Then next, what are we trying to do here? If we're trying to show they bisect each other, we need to show that these two segments would be congruent by maybe corresponding parts, so congruent triangles, or these two would be congruent to each other by being corresponding parts of congruent triangles. We could show possibly these two triangles congruent, the hourglass triangles, or we have enough information, I believe, to show these two, the butterfly triangles, congruent. We can go either way, because each pair would contain these segments that we're trying to prove congruent as corresponding parts. So let's go with, just go with the top one and the bottom one here, just for convenience sake. Let's just go with the hourglass triangles. We'll call this angle 1 and angle 4 up there. If those lines are parallel by the definition of a parallelogram, then angle 1 is congruent to angle 4. Likewise, for the same reason, along the green transversal, this angle in here we'll call angle 6 congruent to angle 7. And again, that's because if parallel lines are cut by a transversal, then alternate interior angles are equal. That would be theorem 6.1, I believe. Theorem 6.1. And next, we're trying to prove, remember, these triangles congruent so that we can show the corresponding parts congruent. So what do we need now? We've got angle 4 congruent to angle 1, and angle 6 down here congruent to angle 7. We also know from a previous theorem now that opposite sides of the parallelogram are congruent. So CD is congruent to AB. CD is congruent to AD because of theorem 13.1 we just had, which says that opposite sides of a parallelogram are congruent. So that makes this congruent to this. Now, the hourglass triangles, the top one and the bottom one, would be congruent to each other by angle, side, angle. Let's call this point in here of intersection a name like M. So now we can say triangle DMC. Triangle DMC is now congruent to triangle BMA. And that would be by angle, side, angle. So now it opens things up to do what we want to do. And that is, we can now say that DM is congruent to BM because they are the corresponding parts of the two congruent triangles. And by the same reason, AM is congruent to CM. And again, that's because they are corresponding parts of congruent triangles and they are therefore congruent. So, since these two pairs of segments are congruent, then we would say that M must be the midpoint. M must be the midpoint by definition of what a midpoint is. Definition of midpoint, which says a midpoint divides a segment into two congruent parts. In the previous step, we just showed they were congruent, in fact. So if M is the midpoint, then that means that is the point of bisection. So that's the way the final proof was worded. We have to prove that they bisect each other. So M is the midpoint, therefore BD and AC bisect each other. They bisect each other because of the definition of a bisector. The definition of a bisector says that B-I-S-E-C-T-O-R. Definition of a bisector says a point is a point of bisection if it divides it into two congruent parts. So if it's a midpoint, then it must be the point of bisection. Consecutive angles in a parallelogram are supplementary. Consecutive angles in a parallelogram are supplementary. If we think of this parallelogram as a portion of parallel lines, look at this. Let's extend the top and the bottom side of this parallelogram and extend this side too like a transversal. Remember the theorem that said if two lines are parallel and cut by a transversal, then same side interior angles are supplementary. That's theorem 6.2. Theorem 6.2. So this is just an extension of theorem 6.2. Theorem 6.2 just dealt with parallel lines in a transversal. Now we extend it on into a parallelogram and becomes now a new theorem, 13.4. So any two consecutive angles, we can do this way or over there or that way and show that any two consecutive angles around the block here are supplementary for the same line of reasoning. A diagonal of a parallelogram forms two congruent triangles. Okay, that would be easy to do if we draw this diagonal here once again. We proved a while ago that they were congruent, and it would also be the same thing that would be true for the other diagonal. Let's do the longer diagonal this time. Again, this diagonal forms two congruent triangles. If we draw the longer green diagonal this time, by definition, these opposite sides of the parallelogram are parallel. So that makes this angle and this angle congruent to each other. And because these two lines are parallel, that would make this angle congruent to this angle. That's because AD is parallel to BC. So looking at it this way, that green line is the transversal across those two parallel lines. Now, the green line itself is a common side between these two triangles, so therefore the triangles are So once again, here's a summary of what we've just gone through. How can we say that a figure, a four-sided figure, is a parallelogram? Again, number one, by definition, show that both pairs of sides are parallel. That's by definition. We could show that both pairs of opposite sides are congruent. That's by theorem 13-6. We could show that one pair of sides is both parallel and congruent. That's by theorem 13-7. We could show both pairs of opposite angles congruent. That is by theorem 13-8. We could show that consecutive angles are supplementary, and that's by theorem 13-9. Any two consecutive angles supplementary. And last of all, we could show that the diagonals bisect each other. That would be enough to show that this is a parallelogram, and that is by theorem 13-10. So there's a summary of ways to show that a four-sided plane figure would be a parallelogram. If two lines are parallel to each other, then all the points on one line are equidistant from the points along the other line. Think of the lines along the edges of a highway. They have to always be equidistant, apart from each other. Think of a window frame or a door frame. You know, the opposite sides must be equidistant from each other, otherwise that window or door is not going to fit. But again, if these two lines are parallel, then every point along here would be equidistant to that other parallel line. And the distance, you know, from a point to a line is the measure of the perpendicular from that line, from this point to the line. So any other point along here would be the same distance to that line. Any point down there. So if we took a measuring stick of some type, all the way across there would be the same distance apart. Theorem 13-12 says, if three or more parallel lines cut off congruent segments on one transversal, then they cut off congruent segments on every transversal. Let me show this to you by this little stick model. If these parallel lines, these are all parallel lines going across here, if they cut off equal segments along this transversal, if somehow we knew that this was 3 inches, and that was 3 inches, and that was 3 inches, and that was 3 inches, 3 inches, and 3 inches, all the way down, then any transversal that would slice across these parallel lines would be cut into equal segments as well. This might be 4 inches, and that would be 4, and 4, and 4, and 4, and 4. So any way you slice it, the corresponding segments, of course, down the transversal would be congruent. Okay, let's figure out some angle measures here by only being given this information here. Here again we have a parallelogram. You can see the opposite sides are marked as parallel. So with that information, knowing that it is a parallelogram now, let's see if we can figure out the measures of all the remaining angles. Well, if this is 30 degrees, then this is 30 degrees. And again, there's really no logical order necessarily that this has to go in. I could start maybe with another angle and go around it another way, but it'll still arrive at the same final conclusions. So there's no magic in the order in which I'm going through this. So if this is 50 degrees, that makes this 50 degrees because they're equal alternate interior angles with that transversal. And in this upper triangle up here, you see 50 and 30 degrees, so that means the remaining angle must be 100 degrees, total sum of 180. If that's 100, then this has to be 100 degrees because vertical angles are equal. And these two are adjacent angles that are a linear pair, therefore supplementary, so that's 80 degrees. Same thing over there then, because those are vertical angles, 80 degrees. Now, in this triangle over there, we know that's 80, that's 40, so what has to be left over would be 60 degrees down in there. And if that's 60, then this angle has to be 60, because those are equal alternate interior angles. Also, if this is 40 degrees as given, this angle here is 40 degrees, because they are equal alternate interior angles. So a lot of these are all intertwined there, as you can see. Okay, by some of the more recent theorems there, if these parallel lines cut off equal segments along this one transversal, remember the theorem says it cuts off equal parts along each and every transversal. So if this is 12, 12, and 12, and we know the measure of one of these other segments, we know that must be 10 and that must be 10, easily enough. And likewise, if that part there is 15, then that makes this 15 and that 15, because they are all transversals which slice the same set of parallel lines. And last of all, here we have a combination. If this is the segment which connects the midpoints, which is 24, then we say this is parallel to this side, and it is 1/2 the measure of that side. So if this is 24, then this has to be 48 in measure. If this is 70, then this angle is 70 degrees, because these being parallel makes these equal corresponding angles. If that's 70 and that's 60, the remaining angle there is 50 degrees. That makes this angle be also 50 degrees, because of equal corresponding angles. In our next lesson, we're going to carry on with our parallelograms and specialize in the subset families of parallelograms, the rectangle, the rhombus, and the square.